Our planet, the third from the sun in the solar system, has the vital properties that make life possible. One of the most important of those properties is the ability to absorb and store energy from the sun, an energy source that is 93 million miles away. The Earth is a giant solar collector, and the energy stored in the Earth is renewed every year. The emergence of geothermal heat pumps, or GHPs, is making renewable geothermal energy available to everyone. Heating, cooling, and water heating using the Earth's energy is one of the most exciting stories in today's world of rapidly changing technology. Employing the same principles as the familiar air source heat pump, GHPs take advantage of the Earth's relatively constant ground temperature to provide low-cost heating, cooling, and water heating for homes and commercial buildings. Live from Oklahoma State University, welcome to Geothermal Heating and Cooling 1993. And now, your host, Ron Dahlgren.
Welcome to Geothermal Heating and Cooling 1993. This is the second of three conferences. The first was held in July of 1992. The sponsors of these National Geothermal Heating and Cooling teleconferences welcome you to the first of two 1993 conferences. Before we start today's program, let's go back and review a little of the 1992 program. Here are some of the comments by Bill Hecht of Pennsylvania Power and Light and Con Abney of the International Ground Source Heat Pump Association, taken from the July 1992 teleconference.
Geothermal technology deserves a place in our national energy strategy. It certainly has a place in PP&L's energy strategy. We view geothermal heat pumps as the most energy efficient and environmentally sound space conditioning technology available today. That's why our company has a goal to increase the number of annual geothermal installations tenfold in the next 5 years. For example, by 1996, we expect that a quarter of the new electrically heated homes in our service area will have geothermal systems. And that's just the residential market. PP&L supports geothermal technology because we're convinced that it's in our best interests, in our customers' best interests, and in the nation's best interests. For us as a utility, high efficiency is just one of the benefits of geothermal heat pumps. For starters, high efficiency means an improved load factor. Since ground source heat pumps operate at the same efficiency day and night, winter and summer, they place a relatively smaller demand on the system during peak periods. This lower peak demand enables us both to defer the construction of new generation and to provide a more stable use of our existing facilities.
The utility in a lot of situations can use this as a competitive marketing tool in competitive sales against alternative fuels, while at the same time it can be used as a demand-side management tool in the efficient utilization of installed capacity.
Today's conference is designed for an audience of dealer contractors, well drillers, home builders, and others who are involved in geothermal heat pump installation or might like to be. Today we're going to hear some success stories from contractors who are making a business of geothermal heat pump installation. We're going to review what's new, show you some actual geothermal heat pump installations, and tell you about sales, equipment design, selection, and installation. In the July 1992 teleconference, the U.S. Environmental Protection Agency mentioned several points from a report they were developing on advanced HVAC systems. Today, Michael LaCour of the EPA is in New York State to announce, in conjunction with the New York Downsite program, the availability of this report. Here on tape is Michael LaCour to make that same announcement for the rest of us. Mike.
Thanks for the opportunity to tell you about EPA's new report. It's called Space Conditioning, the Next Frontier. In this report, we compared several different kinds of residential space conditioning equipment, both standard and advanced. We even looked at some equipment that's not on the market yet, and we did it in 6 representative locations around the nation. Among the technologies we analyzed, of course, were geothermal heat pumps. In the analysis, we compared these various systems as to their seasonal operating performance, their cost to consumers, their environmental impact, and their cost effectiveness for utility programs. For those that looked most promising, we estimated how aggressive utility programs might increase their potential market penetration over the next decade or so and yield cost-effective pollution prevention. We found that there is an awful lot of economic and environmental promise from advanced heat pump technologies, and in many respects, geothermal heat pumps led the pack. For instance, geothermal heat pumps had the highest net heating and cooling season operating efficiencies in all the locations we looked at, even considering the losses that electric energy experiences in generation, transmission, and distribution. We found that geothermal heat pump systems reduce energy consumption by about 1/4 to 1/2 over standard air source heat pumps, and by 2/3 to 3/4 over electric resistance systems. Because of these high operating efficiencies, geothermal heat pumps had the lowest emissions of carbon dioxide, the main culprit in global warming. We also found that geothermal heat pumps generally were very cost-effective for promotion in utility conservation programs. In fact, if utilities around the nation formed aggressive programs to promote both advanced geothermal heat pumps and the most advanced air source heat pumps, which are also very cost-effective in the South, they could have a huge effect on shifting the market. We estimated that the total market for advanced electric heat pumps together would grow to over 700,000 units per year by the year 2000, with 300,000 of these being geothermal heat pumps. By the year 2005, as consumers became more aware of their benefits, the demand for geothermal heat pumps would grow to well over 400,000 units per year, outstripping the demand for air source heat pumps. Now, if this market potential were actually realized, we as a nation could save 23 billion kilowatt hours a year by the year 2000 and avoid the need for 25,000 megawatts of generation. That's about 83 new power plants. Carbon dioxide emissions would be reduced nationally by over 17 million metric tons. Smog-producing nitrogen oxides would be reduced by over 45,000 metric tons. And sulfur dioxide would be reduced by 70,000 metric tons. While their emission benefits were not as high, EPA also found plenty of cost-effective pollution-preventing potential with advanced gas technologies as well. So now, what is EPA planning to do with this information? Well, we'd like to make these good things happen, and we are beginning to work to do so. On the day after the teleconference, I will be meeting with Niagara Mohawk and other leading utilities from the Northeast to explore the design of a national initiative to pool the market power of utilities to promote advanced electric residential space conditioning equipment. By working together, utilities can provide industry with clear, consistent, and sustained demand for their very best products. 25 utilities from around the country working together with EPA and environmental groups on the Golden Carrot Super Efficient Refrigerator program have already shown that this approach really works. It's time to start using it for advanced space conditioning equipment as well. Please get in touch by ordering the EPA report, which is now going into print, or by calling me at 202-233-9127. Thank you very much. I hope you enjoy the rest of today's teleconference.
All right, thanks, Mike. There's an order blank for this report in your registration materials, and if you want a copy, send the order blank directly to Michael in Washington. Today's program is going to be broken into 3 parts, with opportunities for answers to questions that you phone in between segments. You can call anytime, starting right now. The number is on the screen. Our operators will take your questions and relay them to the appropriate panelist. First, you'll hear from some contractors who are installing geothermal heat pumps today. They'll tell you what it takes to get into the business and how they view the future of the geothermal industry. We will break to answer your questions for these contractors about 15 minutes from now, so call us with those questions. After that, we'll tell you about the questions homeowners and building operators asked when they were considering a geothermal heat pump. In answering those questions, we'll take you through the installation of geothermal heat pumps in residences, commercial buildings, and institutional buildings. Then we'll break to answer questions again. Lastly, we'll tell you about new developments in geothermal heat pump technology and installation and where to go for information and training. We'll close the program with another opportunity for the panel to respond to your questions. So let's get to it. In the studio today, we have 3 successful contractors who are available to answer your questions and offer you the benefits of their experience. These contractors represent the range of activities that are involved in the geothermal heat pump business. With us today are Ralph Cadwallader of Loop Tech International and Bill Van Alstine of Van & Company and Lynn Vick of Aero Heat and Air. Ralph Cadwallader concentrates on installation of loops and has been involved in a large number of installations in the Austin, Texas area. He has drilled over 1 million feet of borehole for geothermal heat pump applications. Currently, he is working on the Bailey Middle School project in Austin, where he is installing a 600-ton ground heat exchanger. In this large installation, each heat pump system or comfort zone has its own circulator pump and ground heat exchanger field instead of a large central pumping station.
We were awarded this contract for the Gordon Bailey Middle School here in Austin, Texas. This is one of the few projects that we've done here. Of course, this is the largest. It's 532 tons of cooling capacity, and all of it's earth coupled. It's the largest unit being 35 tons, and then the console units being 3 tons. The boreholes here are anywhere from 265 feet to 290 feet, and we have approximately 22 miles of borehole and a little over 50 miles of polyethylene pipe in the whole piping system. The formations here is the Edwards Aquifer. It's very difficult drilling. We have caverns and caves, and it's rock for the whole 265, 290-foot bores. The backfilling process, of course, we're using a cement slurry because the holes are dry, and we're able to backfill them. We feel like we'll get the best heat transfer that we've had in any of the projects we've done here. This is quite an undertaking. As Bob said, one of the largest projects and the largest one in Texas. And we're quite pleased with the way it's turning out. We only lack about 34 more boreholes before we complete this project, and this school will be ready to turn over. And as the school district's very pleased with the results of the low maintenance and the utilities. The rooftop units have been eliminated, all the penetrations. There's no outside equipment that can be vandalized. There's just a lot of opportunities here for aesthetics, making just a better system overall.
We're in one of the 4 mezzanines at Gordon Bailey Middle School that house the large units. The one I'm sitting in front of is the 36-ton heating and air conditioning heat pump. I want to draw your attention to the polyethylene coming through the floor, the 2 4-inch lines coming through the floor, terminating at the flanges. All of our interior piping is done through polyethylene pipe, except for what you see here. Fewer fittings, fewer valves, less chances, opportunities for a leak. The 4-inch pipes come directly from the well field, manifolded and headed together. This is all one system. It's not valved exterior. It's all unitary. It's all one system. We after that, you see the isolation valves of the well field and the 2 blue handles, which are the purge valves. The purge valves we use to purge all of the trash out of the system, to purge all of the air out of the system by maintaining in excess of 2 feet per second through the entire system. On a 36-ton system, that takes a tremendous amount of water flow. But that is doable. We do that. Then you'll see an inline circulator, this large Grumpus inline circulator that provides the pumping to circulate the water to maintain our 3 GPM plus or minus per ton of air conditioning. and isolation valves. You'll also notice piece ports on both sides of the unit, both sides of the pump, to give our pressure to be able to get our pressure differential across the pump. Also, we have piece ports where the lines come in and go out of the air conditioning unit itself to be able to get pressure differential, in addition to temperature differential to find out the effectiveness of the field, effectiveness of the air conditioning unit itself. As you can see, it's very simple. It's very low-tech technology. You don't see any expansion tanks, makeup water. We pressure up the system to 60 psi, and it's only that high of a pressure mainly to be able to accommodate the differences in the heating cycle and the cooling cycle. The fact that the pipe walls expand and contract faster than the water itself does. Again, it's very low-tech technology. The large units are doable. There's nothing mysterious or difficult about them if you have the right training and equipment to be able to work on the systems.
Bill Van Alstyne is a loop contractor and a full-service dealer in ground source technology. As well, Bill installs both vertical and horizontal geothermal loops on a contract basis. He is a licensed well driller. The largest job he has done is the drilling and installation of the geothermal heat exchanger for the State Capitol building in Oklahoma City. R&M Mechanical Contractors had overall responsibility for the mechanical system installation. Here are details of the building and the ground heat exchanger installation.
The State Capitol building of Oklahoma is an historic building with approximately 400,000 square feet of floor area and 6 floors. It was initially cooled by window air conditioning units and unitary air conditioners and heated by steam from a steam generator located near the building. A ground heat exchanger was installed inside a 300-foot diameter traffic circle and consists of 373 vertical boreholes, each 256 feet deep. A maximum of 6 loops are attached to each header pipe, which are connected into 12 underground gathering pits. Supply and return lines from the field run under the traffic circle through an existing steam tunnel. Fluid from this field is circulated to 325 heat pumps located throughout the State Capitol building. 2 125 horsepower pumps operating as a primary and standby arrangement are capable of producing 2,200 gallons per minute each at full flow. These pumps circulate fluid through the ground heat exchanger and the installed heat pumps. There is no intermediate heat exchanger separating the ground heat exchanger fluid from the heat pump fluid. A cooling tower was installed to reduce first cost and waste excess heat that is presently not being used. Ground heat exchanger costs average $5.30 per foot, which does not include the steep pipe from the field to the Capitol building. Drilling of the ground heat exchanger field using a single drilling machine took a crew of 3 persons approximately 6 months.
Lynn Vick is a full-service contractor and installs heat pump equipment, ductwork, and ground heat exchangers. He, like Bill Van Alstyne, installs both vertical and horizontal geothermal heat exchangers and is now installing the new Slinky heat exchangers you'll hear about later in this program. The following video details some of Lynn's business and installation practices.
The initial startup cost, if you went and bought everything new, would probably run $100,000. My personal experience is I bought everything I've had at auctions and looked around, found bargains, bought it a little at a time, and built until I finally had everything I needed. I probably got into it in the neighborhood of $35,000, $40,000. The major problems that we run into when working on these, not necessarily the ones I put in, the ones that other people have put in that I go look at, they're undersized. They're either undersized or it's the loop. Very seldom is something wrong with the unit. The biggest problem I see is somebody has a 2-ton unit. The contractor goes out, puts a 2-ton ground source in. 2-ton ground source on heating will not produce enough heating load for the house. Typically the heating load's twice what the cooling load is. So the heating load needs to be taken into consideration when you're figuring one of these. Some of the main advantages of using the slinky ground heat exchanger is it cuts down about half on your trenching cost versus a two-pipe. One of the main problems with a slinky is when you install one, you need to make sure that you backfill the trench, either with sand or by hand, especially in clay ground. If it's not backfilled properly, the system will not work until you get sufficient range to pack the trenches in. In my experience, it takes approximately a year before them to get packed good around all the pipe. In clay ground where it's really, really bad and it's in the summertime, and we've got to have the machine up and running when we leave, we usually haul in sand and put around all the pipes. When we sell a job at the office, we actually build the slinkies right in the parking lot. Or during off times, I have guys out building the slinkies. What they do is they'll build the slinkies, tape them together with duct tape, fold them up. I've got a 16-foot flatbed trailer that we haul the tractor on. We can throw 10 or 15 500-foot slinkies on this trailer, put a tractor on top of it. When we get to the job, I can do the digging, or whoever's running the trenching machine can trench and lay the slinkies in the ground. That allows the other persons to be changing out the equipment, so it doesn't tie up two people outside, one building a slinky and one actually running the trenching machine. And when we get on the job site, we've got everything ready. All we have to do is dig a trench, lay it in, and cover it up. Under normal ground conditions and weather, a typical 3-ton slinky should be able to be dug in approximately, covered up, piped into the unit with the pumps. If the ground conditions are acceptable. There's a lot of them that we put in a half a day, a 3-ton system, put in a half a day, piped them into the unit, hooked the pumps up, and antifreezed them. And we've left the shop at 7:30 and back to the shop by 2 o'clock, and had the entire 3-ton system put in that length of time. A 5-ton, under normal conditions, you know, a day, you can figure a day to put a 5-ton in. Any slinky between 1 through 5 tons should be, you ought to be able to dig it in a day, fuse it together and hook all the pumps up and have it running in a day without any problems.
While we were talking with these contractors, they stressed to us the following important points, which we will summarize before we open the program for your questions and our replies. Keep your operating overhead low. Don't commit a lot of money for equipment until the market develops. Start with horizontal systems if the geology in your area permits trenching with a chain trencher or backhoe. It's less expensive than buying a drilling rig and obtaining a drilling license. Team with a utility or school board group to support your operation. Develop a good working rapport with mechanical contractors. Don't be a competitor unless you are a full service dealer that does the heat pump installation and the ground loops. Make a site plan and a site survey sheet marked with underground utilities. Downtime resulting from repair work costs you money. Call before you dig. Have a clear understanding about who is responsible for restoration work. This can be expensive and a major source of misunderstanding. Have heating and cooling loads available to check on adequacy of ground heat exchanger design. When things go wrong, you will get some of the calls and some of the blame. Successful contractors identified the following equipment necessary to get into the business. Get a drilling rig if you have a license. Start with a top head drive drilling rig. You need a front end loader to remove drill cuttings, and a small dump truck or trailer to remove cuttings from the job site. For horizontal loop installation, a trencher is best. Geology determines the size of equipment. Maneuverability is important. You have to have purging equipment for air and debris removal. If the equipment is too small, time is wasted waiting to complete the job. Grouting equipment is necessary to seal vertical boreholes. State and local rules will determine what grouting requirements are necessary. Everybody should have loop pressure testing equipment to test for leaks as a result of shipping damage or incorrect soldering of indoor piping. You have to have plastic pipe heat fusion equipment, socket and/or butt. Either method is acceptable if performed by qualified and trained personnel. With this introduction, we'll now open the program to the question and answer portion. Our first question is addressed to Ralph Cadwallader. Ralph, how do you decide when to use multiple ground heat exchangers or a single ground heat exchanger field with central station pumping?
Of course, a lot of it has to do with the physical layout of the building or the installation. If it's a large commercial building, you have to take in consideration zoning of the building, and of course, where are you going to put the loops, whether if they're going to be vertical or horizontal. You have to have green areas or parking lot. And all this, depending on how far it is from the building and how you're going to get the water from the loop field to the building and how you're going to distribute it, determines if you're going to have multiple. Now, the school district likes to have, in Austin, likes to have single loop systems for each unit. That way, if they had a problem, it'd only be one classroom. Of course, in some situations, you can't get close enough to drill in that particular instance. So a lot of times you have to go to a large loop field to take care of the whole building.
Okay. Bill, what was the largest job you did previous to the State Capitol project?
The largest job we completed was probably Langston University, the White House at Langston University, which would have been in the neighborhood of 40 to 50 tons at the time. That was all vertically bored drilled. It was installed under a parking lot area and a green area outside the building before the final construction phase. And with one large well field, with a number of smaller circulators connected to the well field that is distributed through the building to the separate heat pumps.
Okay. Lynn, let's go to you. Wouldn't it be more economical to have trenching done by other folks instead of having your own equipment?
Well, I think a lot of that would depend on how many water source heat pumps you're going to put in. If you're going to put a few in, it'd be more economical to have somebody come in and do the trenching for you. If you're going to put quite a few in, it's a lot. In the long run, it'd be better to get your own equipment. Because of scheduling problems, you have to depend on somebody else to show up at the job site. And if you're going to get in the business and do a lot, it'll be better to have your own machines.
Okay. Homeowners ask contractors some of the following questions. Who's responsible for restoring my yard after the ground heat exchanger is installed? Lynn, how would you answer that question?
A lot of the homeowners, that's an individual type problem that if you put them in the country, where most 90% of ours are, it's not that big a problem. Most of them are in pastures. When you have a nice landscaped yard, that is a real problem. What we usually do is we tell the people it's going to be X amount of dollars to come back in 3 or 4 months, bring a tractor in and level the yard back up, because there is going to be a certain amount of settling. No matter what you do, there is going to be settling. And we try to make the least mess that we possibly can when we're doing the job.
Okay. Bill, how would you answer the question from the homeowner says, what is the system going to cost and how long will it take for it to pay back?
If we're talking about just the cost of the earth coupling, basically our cost in my area, and I have to qualify this because depending on where you're going, but I operate mostly in western Oklahoma and northern Texas, and the cost in my area are running for the earth coupling between $600 to $750 a ton. Payback of this amount over a very good air source heat pump would be anywhere from 3 to 5 years of that cost. If I'm installing the equipment as well as the earth loop, once again, it's about the same. Of course, you've got the equipment in your bid, and basically with my rural electric, with their rates and the electric utilities I'm working with, 3 to 5 years is fairly normal for payback, complete payback for the difference of the cost of the systems.
Okay. Lynn, let's go back to you. What do your customers complain about, or what objections do they raise when you're selling a geothermal heat pump system?
One of the most complaints you have is on the outside landscaping. As far as equipment, we very seldom have any complaints. There's a few concerns when you first visit with them. Will it go in the closet? What does it sound like? Various questions like that. The biggest concern is what is going to happen to their yard.
Okay.
A lot of these yards are nicely landscaped, and that's probably the biggest concern we have.
Okay. We have a question called in from one of our sites, and this, I suppose, could be a complaint. This individual would like to know, or says that rodents are chewing through the ground loop. What can be done, or what recommendations do you have? And I'll open that to either of the three of you that'd like to tackle that. Ralph, you want to take a shot at it?
Well, I don't do a whole lot of horizontal, and I haven't had that problem, but my suggestion would be to get your headers or your piping a little bit deeper, because rodents, I would assume, would have a certain range that they would burrow, and I would think that would take care of the problem. But we haven't had that problem.
Bill, Lynn, you want to add to that?
Once again, of all the installations we've installed, I don't know of a system that has ever been eaten into by a rodent. So I think this may be a specific case for this homeowner. And I tell him, kill the rodent, trap the rodent. But if you can, like Ralph said, if you can get to the header system where it could be moved a little bit deeper, normally speaking, rodents, depending on if you're talking about the common gopher or wherever you're at, very seldom burrow deeper than, I believe, in the 2-foot range. So this would be new to me.
Okay. Ralph, what are the positive things that your customers talk about after you finish the installation?
Well, I would think that a customer would expect something positive after he's spent this much money on a system, and he has the right to expect something in return. I think one of the things that he can look at, and they're anticipating, is saving of energy and also saving on maintenance, which these water source heat pumps will benefit in the fact that you don't have any problems with the mechanism or the machine itself, because it's much like a refrigerator. I think that the life expectancy is going to be longer, and they can enjoy the fact that they won't have that cost of replacement equipment. Okay. Another thing would be a greater comfort. These water source heat pumps provide a very comfortable heat and do a real good job on the humidity control, and so the result is greater comfort. And I think the third thing would be aesthetics. You know, you're going to be doing away with your outdoor equipment. You won't have to listen to it, you won't have to clean up around it or worry about the weather deteriorating it. And these are some positive things that I think that they can anticipate for the amount of money that they've spent on the system.
You bring up something that I've heard. I have a good friend who has a system, and the thing that he praises all the time is how quiet it is. He absolutely loves that aspect of it. Well, apartment complexes like the Park Chase Apartments in Tulsa, Oklahoma, are prime candidates for geothermal heat pumps. This apartment complex needed a new heating and cooling system since the boiler and chiller were old and operating inefficiently. After a one-year project development process, the Department of Housing and Urban Development is installing 413 ground source heat pumps. The 537-ton GSHP renovation project is scheduled to be completed March 31st, 1993. Public Service Company of Oklahoma put together a team of GSHP experts, contractors, and manufacturers to work with the consulting engineer on the GSHP concept. HUD's decision to upgrade the thermal energy integrity of the apartments had a dramatic effect on the energy cost and utility benefits for the project. HUD spent $244,000 on these improvements, but saved $396,000 immediately on the reduced tonnage requirements for the heat pumps. Because of these improvements, the peak summer demand is expected to be reduced by 280 kilowatts, and utility costs are forecasted to be lowered by $40,000 per year. New construction, Philip Lee Russell, owner, Russell Lee Home Builders.
Well, when we took over this apartment complex, it's a large, for us at least, a large complex of 348 units. It was heated and cooled with a two-pipe system, chilled water and heated water. The system is 27 years old, I think. Many of the lines were plugged. The whole system was inoperative, and we found out that a lot of the equipment was installed used some 27 years ago. So we were faced with a total replacement of the HVAC system. We had people heating their units with open flame kitchen stoves for last winter. We wanted the best and the cheapest and the best thing for the government, so we hired an engineering firm here in Tulsa to evaluate the entire system, evaluate the whole thing. They evaluated every option, from gas to combinations of gas and electric to all electric to heat pumps, everything. They came to the conclusion that the most economical thing for the government, and part of this is somewhat based on the fact that we got some cash rebates and some cash benefits from the utility company, was the ground source heat pump. The simplicity of the thing sold me on it, particularly the ground source heat pump. It's a lot more simple than the air-to-air. The air-to-air is nothing like the ground source. The unit that we buy is just like almost like a window air conditioning unit. You just plug it in, or it's charged, or there's no filling it with Freon in the field, and overcharging and undercharging, and escape of Freon, which has become an issue. So, and the people that we talk to have nothing to do.
The gas, hot water, hydronic system, it had a lot of favorable features, but it just really in the long term couldn't compete with the heat pump systems for this project.
The role that I play is working in combination with the utility companies like Public Service Oklahoma and the Electric Power Research Institute. We're looking for subdivision programs where we can demonstrate this technology in different areas of the country and different kinds of projects. The HUD project here is an example of a kind of project that we feel like has quite a bit of promise. You have a well-distributed area where the buildings are placed. It would be difficult to come in there with a chilled water system because of the underground piping and existing utilities that are here. It's an example of a kind of project where the ground source technology is well suited. Distributed buildings where it's easier to come in and add modular type of units in the various buildings and put that all together in a package that probably has an efficiency higher than anything else that we could do.
We were trying to reduce the glass area in all buildings. All the windows on the project were single-hung, non-insulated windows. We had a lot of conditions where we had 3 of those windows side by side. What we did was we took 2 of the windows out and left 1 in. Actually, the one that was left in, it's a new window. It was a double-hung insulated window.
3 very, very intelligent and basic questions. The first question was it comfortable? Were the people and the tenants that lived in the apartments comfortable in the geothermal apartment complex, or the earth-coupled geothermal apartment complex? And the answer to that from the maintenance department was yes. There's 100% occupancy in the geothermal building. The other 2 buildings, which consist of window air conditioners and central furnaces, did not have 100% occupancy. There was a waiting list that if anybody left the geothermal apartment complex, the existing tenants from that property wanted to move into the geothermal building because of its comfort. The second question that Mr. Beck from HUD asked the maintenance man is reliability. What was the maintenance track record on the geothermal system? The answer to that is the 2 existing gas heating and electric air conditioning had a preventive maintenance contract and an annual service contract with also additional service calls throughout the year. The geothermal system, being 6 years old, has no maintenance contract, probably 2 or 3 service calls over the last 6 years, and all the maintenance facility does, or maintenance crew does, is change the filters, that's all. The third question that Mr. Beck from HUD posed to the maintenance man was about utility bills. And that answer was very simply put, that the geothermal building costs approximately half the utility bills that the other two buildings have. And so in a nutshell, the three items that were most concerned to HUD, comfort was answered, dependability and reliability and from a service standpoint was answered, and operational savings of up to 50% was answered.
All right. We have another question that's been called in. This one comes from the Public Service Electric Company of Newark, New Jersey. Bill, while we were in that tape, you said you would take the first shot at this. What and how often is maintenance required on loop systems? And if possible, can you give a breakdown on the different types of loop systems? And do some have less maintenance requirements than the others?
Okay, begin with on the maintenance of the loop system should be the loop system itself is zero. After a loop is installed, possibly within the first 12 months of its installation, you may need to come back and actually repressure the loop or check the pressure on the loop. But if the loop is installed correctly, then basically it's permanent. It should outlast the building that was installed on, and there's no maintenance on it. Everything's buried on it. Now, the loop circulated pumps are our piece of equipment that could require maintenance. Most of them are water cooled and water lubricated and are very long lasting. Now, as far as the different types of loops, there is the vertical bore, which comes in, of course, we're digging a certain diameter hole, depending on the footages that we need on a building, anywhere from 100 to 200 foot vertical bore per ton, once again, depending on the load. We have horizontal systems. Basically, those are two different systems now. In fact, the horizontals are in several different configurations. The Slinky being the newest one, which varies from maybe as much as 1,000 feet of coiled pipe in a 100-foot trench to as little as 500 feet of pipe in a 125 or 30-foot trench, once again depending on the load of the building. Also, another type of horizontal would be the single pipe or two pipe or four pipe. These all can be installed in the horizontal trench. Depends on how much space you have available, what the expertise of the contractor installing the pipe is, cost factor of the pipe. There's a lot of variables there. This is one place where the Slinky is starting to encroach on that type of business because there's less trenching involved, a little bit easier for contractors to install. Did I get all the questions there?
I think you covered it. Lynn or Ralph, do you have anything you want to add to that?
Well, I'd just like to add that, you know, in some instances where you have large installations, you may, like Bill said, you may find a pressure differential, and that needs to be watched in the startup time, because depending if you start up in the summer or the winter time, you'll have some expansion of the pipe more so than you will of the water, and your pressure will vary. As long as you have a positive pressure, though, your pumps will be able to handle the workload and be able to work properly. That's one thing that needs to be watched. But as far as maintenance on a loop, we're expecting the life to be anywhere from 7,500 years. We don't know. My loop's been in my house for like 12 years now, and I haven't even been back to check the pressure. But we feel pretty good about our fusion techniques. And if it's all done properly, you shouldn't have to even have makeup water on these systems, and as a result, you're not injecting oxygen or any type of corrosive. And since all of our material is designed for no deterioration, you shouldn't expect or have any problems with your loop system.
All right, fair enough. Thank you, gentlemen. Philip Russell, owner of Russell Home Builders in Florida, has been successfully marketing his homes using geothermal heat pumps as an added benefit. Here are some comments from Phil Russell about this technology and his business.
Our company normally builds 18 to 20 custom homes per year. And we've specialized in the energy efficient niche, more or less, in this market for the past 14 years. 90% of the homes that we've built in the last probably 5 or 6 years have used geothermal heat pumps, and therefore we appreciate being a part of this national teleconference. Geothermal heat pumps in this area have caught on very well in the last few years. The transfer of technology is easy. Geothermal heat pumps are easy to install. Yes, they do cost a little bit more, but the efficiency level is so much higher that normally when someone comes into our office and wanting a Russell-built home, We don't necessarily sell them on the energy efficiency aspect of the homes. We sell them on their personal comfort level. I find that to be a big selling feature for our homes. They're quiet, comfortable, efficient. The systems are well balanced. They have a good humidity control, and it's a good investment in the future for any homeowner. As I mentioned earlier, 90% of our homes do have the geothermals. There's no outside units to corrode or whatever, and everything is more or less in a prepackaged unit. They're just an environmentally friendly type unit.
PSI Energy of Indiana was one of the first electric utilities to initiate a subdivision program to demonstrate that installing geothermal heat exchangers prior to construction could reduce installed costs. The results of the Walden Pond demonstration subdivision have prompted PSI Energy and other utilities to develop other all-geothermal heat pump subdivisions. The beneficial results of lower installed costs, demand reduction, and cost benefits to the utility are described by Jerry Brandon of PSI Energy.
The goals of the subdivision program that we now have in place at PSI Energy were two main ones, and one was to get the cost of loop installation down. We've been successful in doing that. Our cost for loop installation now runs between $450 and $475 for horizontal installations and $900 to $1,100 for vertical installations. That includes the installation of the pipe, the cost of the pipe, and the antifreeze solution stubbed up to the home. Then it's up to the HVAC contractor to connect to that loop. We've also been able to pick up good DSM impacts. We're getting in the neighborhood of 2 to 2.5 kW peak reduction in the summertime and between 4 to 5.7 peak reduction in the wintertime. It's helped us tremendously to take an organized approach to multi-loop installations in our subdivision program. It's been very successful for us in dropping those prices down for the new home market to the $450 to $500 per ton range, as opposed to the individual installation market in the same area of $600 to $800 a ton in many cases. In our service territory, when you look at comparable, you look at high efficiency gas and high efficiency central air conditioning equipment and compare it with geothermal heating, you're talking about approximately the same amount. You might get a slight premium for the equipment itself on the geothermal in the neighborhood of $200 to $300, but the primary cost difference is in the loop installation. And in our subdivision program, we've been able to subsidize the builder and the developers considerably on that by providing those loop installations for them. We've estimated that the value of an average system GT geothermal heating system going in for load growth to be about $2,200 to $2,600 in present value terms, and for demand side management benefits for avoided cost and energy in the area of $3,000 to $4,000 in present value terms.
All right, we have a few more questions that have been called in for our contractors. This first one comes from Al Papani, and I hope that's a correct pronunciation, from Newburgh, New York. He asks, when heating loads are twice that of cooling loads, what about humidity control in the cooling loads? Would the heat pump cool too fast for humidity in the Northeast, specifically, again, from New York State?
I've been volunteered to answer that. Usually, you'd want to look for a heat pump that would have a variable speed blower or possibly a two-speed earth coupled unit in this case. That way you'd have it would have the capacity to put out the higher heat load, yet in the low speed or in the variable speed with in the case of a variable speed blower on a single speed scroll compressor, reciprocating compressor, you'd have a much lower air volume and better humidity control in the summertime. And we've had several cases of that, and usually that's a very good solution for that.
All right. Another question from Fort Smith, Arkansas. What warranty is there on the pipe in the loop system, and what does that warranty cover? There's a concern about shrinkage and shrinkage of the soil and what damage that may do to the pipe. Let's tackle that, Ralph.
Hey, well, I don't know of any problems as far as shrinkage causing damage to the pipe. We have some very abrasive formations that we have been installing loops into and have not had any problems. The product that we use, of course, the high-density polyethylene, is very tough and has high strength, and it's really, we feel like, the proper material to use. So we really haven't encountered that problem. But as far as warranty, there are some manufacturers pipe manufacturers that put out a 25-year warranty. There are some equipment manufacturers that have even gone further and given even a 50-year warranty. As far as our company goes, we use a high-grade polyethylene from 2 manufacturers, and we give a 5-year labor and material warranty as far as a contractor. And then if the pipe manufacturer wants to pick up and even extend that, you know, obviously that's their call.
All right. Is there a recommended size on the pipe for loop, 3/4 inch, 1 inch? This question comes from Frank Jones of Wichita Falls, who's watching in Arlington, Texas.
There again, it depends on the application. It's even been studied that larger diameter pipe is able to transfer more heat. Of course, the more surface area you have, the better ability you will have to transfer heat. One of the things that comes into consideration is your head loss in determining your pump size. We want to use the smallest pump available to lower our operating costs, so we will size our pipe accordingly. In some instances, when your borehole is shallow, we can use a 3/4 and do a very effective job. Now, when you get into installations like in South Texas, we'll even be at 300 feet per ton. We have to go to 1-inch pipe in order to reduce our head loss. But one of the things you got to be concerned about also is the amount of flow so that you don't get laminar flow. We feel like if you keep the velocity up to a certain extent, you get your better heat transfer. So it's really a design call, and it depends on the geology and the application.
All right, gentlemen, that's it for that run of questions. Thank you. Building owners and operators have realized the benefits of geothermal heat pumps, and their comments on what the advantages of these systems have are as follows.
We initiated the ground loop program in 1984 at one of the additions to our schools, and we were well pleased with it after discovering we had a low maintenance rate and a low utility rate. And so from that we proceeded to install in 4 more additions that we did in 1987 and 1989. And from there it just grew kind of like wildfire, and now we have some 49 renovations in the school districts that we've done with the ground loop system, and we have 5 new elementary schools that are coming online or already online with the ground loop system, and not including the one we're at right now, which is the Bailey Middle School project, which is our largest project to date, and we think it's going to probably be the most outstanding system we've got in the state at least, and maybe in the whole country. Hopefully. But that's kind of giving you an overview of what we've done in the school district so far. And we're not through yet. We're still putting them in and still bidding them every time I get a little money, I do another school. One thing we strive for in the school district and have been for some time, and I think we finally hit on it, is the individual room control for the teachers. The teachers have complete control of their environment within their room, heating and cooling, and the teachers are absolutely ecstatic about the system. They love it. And the principals, of course, they like it because the teachers are happy. And one other plus with this system, anytime the teacher wants to stay after work, the only thing she has to operate is her own system and not the entire building. We lose one of these units, we don't lose the entire building, we lose that one unit, which is a big plus. With a central system, we lose a chill water pump or a chiller, we're down to the whole school. This doesn't happen with this system. This is another plus. And the teachers can work anytime they want to, after school hours, on the weekend, anytime they want to come in, they can turn their system on and operate it without having anyone's permission or turning the whole building on, which is another plus for the system.
Lynn, we have a question that's been called in from Ohio. This person wants to know, why should a contractor get involved with geothermal if he or she already has a successful business with gas and propane?
More and more so. The reason I got involved in it is because customers of mine that I was servicing their regular equipment kept asking me if I would install it for them. And that's what got me started into the business. And once I started installing it for these people, the word got out, and more people, and eventually that's probably 50% of my business. The electric companies right now, they're promoting the equipment. That's another reason. If you're going to be in the heating and air conditioning business, there's more work available through electric companies to help you put these in.
So really consumer or customer acceptance and demand.
Right.
All right. Let's move now to Louisiana. Louisiana Electric Cooperative in Baton Rouge converted an electric boiler and chiller to a ground source unit. Their savings are impressive and typical of what can be expected. The Bixby YMCA buried their horizontal ground heat exchanger under the parking lot to save space. The lack of rooftop equipment and roof penetrations reduced insurance costs. The geothermal heat pump system has a small equipment room requirement, and the lack of outdoor equipment is a benefit.
I'm Alan Watts of Alan Watts Service Incorporated out of Baton Rouge. We've been installing these ground source systems now for approximately 10 years. This particular project with the Louisiana Electric Co-op was rather unique in a way. We had a certain amount of space to work with. We had to come in, take the lights out and so forth, and we had to try to get the loop system located in this one little area without disturbing any of the existing trees or getting in the way of the lighting systems and so forth. So what we've done is went in, and in this area right here, we have a total of 28 300-foot shaft, or should I say boreholes, which have 1-inch polybutylene pipe in them and then manifold into headers. Have 2 sets of 14 going into 2-inch headers going into the building and so forth, and then tying into a single circulating pump. As you can see, now that the job has been completed and so forth, the ground has been returned to its original condition. The owner was very concerned whenever we first got to talking about putting this system in. He wanted to keep the appearance of his building up. Well, we were able to come in, do the work, and put everything back as it was without disturbing any of his foliage or any of the trees or anything else. Put all the lighting system back where it was originally. This being a retrofit, the owners were very sensitive about keeping the appearance of the building up. We needed to get the pipes over into the equipment room. So what we did was come in and build a metal channel matching the gutter system, bringing it up into the attic section of the building and going on across into the equipment room. As you can see, this is our equipment room now that we've installed the new equipment. We took out 2 old large air handler systems which were real dinosaurs, and extremely noisy and very, very inefficient. Now we have a total of 9 separate units. Each unit has its own zone in the building. Each section of the building has its own thermostat. Now we have basically each area, if you have one area that would like to have a little cooler than another one, well, they can do so. They have their own individual controls. This makes the people in the building a little happier. They're able to operate the total system. As far as maintenance on the system compared to the old system, we've got a few filters that will come in once a month, keep the filters clean, and that's about the extent of the maintenance on the total system. It's a very, very low maintenance type system and very energy efficient. As you can see, all our piping is polybutylene and all brass. Any metal fittings are all brass. It makes for a long-lived system.
Well, naturally, our primary concern was the cost when we went into the project. Our old system had to be replaced, and we could have replaced it as it was for about $40,000, and the new ground source heat pump system was in the neighborhood of $70,000, so there was quite an increase in the cost, and we were concerned about the payback on that and being able to recover our investment. And in fact, as a result of installing the system, we've seen our kilowatt-hour consumption reduced by about 46%, and the actual cost of our utility bill each month has declined about 39%. So in about 3.5 years, we've actually recovered the difference in the cost between installing the old system that we had as opposed to the ground source heat pump. And I can't tell you how much nicer it's been in our building as a result of that. We're extremely pleased with the outcome of our front yard, that it came out exactly like we thought it would. It looks like there's nothing there, and the entrance into our building is much improved. And As a matter of fact, we've constructed a storage building on the slab where the old units were located and are making use of that space too. So we're extremely pleased with the installation of the system, and wish we had done it before we did.
Being in the Y for 20 years, I've had 5 different buildings, so I had some kind of a idea operationally what I wanted. I was concerned about being a nonprofit agency, having the funds every year to run a building at the lowest cost I could find, and also a predictable cost.
When we found out the other pluses of not having the roof penetrations, no cooling towers, no boilers, all the units being located within the building, up above the suspended ceilings, so the units themselves aren't exposed. We got an extended warranty on our roofing, and those were all pluses.
Now, the State Capitol building ground heat exchanger was installed by Bill Van Alstyne and demonstrates that two contractors that are experienced and who do quality work can grow into bigger and larger jobs. Previous to this, Mr. Van Alstyne's experience has been limited to residential and light commercial projects. Bill, did you find that the State Capitol project was a lot different from those smaller projects?
In the basic setup of the State Capitol project, no. It was just essentially the same as doing 150 houses all at one location. Basically, that's the way we approached the drilling. We drilled it with one rig and one crew. We were more or less tied to the building schedule of as the contractor was changing out the equipment inside the building. So actually we kept up. We were able to bring parts of the well field on as necessary to support the equipment that was being installed inside the building. But the difference is we were able to walk right from a residential job right into the State Capitol without any big changes. We did hire a little extra help. I got a little bit bigger backhoe to do some of the digging for me, but other than that, it was a quite easy transition.
All right, thank you. Well, recent advances in technology and applications have led the way to improve system performance and cost. Included in these advancements are vertical drilling equipment to reduce setup time and increase productivity, horizontal boring machines to eliminate yard restoration, new ground heat exchangers to reduce trench length, non-toxic antifreeze solutions to meet environmental safeguards, and variable capacity heat pumps to more closely match heating and cooling loads. Integrated water heating heat pumps to supply domestic hot water on demand. To further explain these new developments, we have 3 studio guests. Our first is Peyton Colley, project engineer with the research arm of the National Rural Electric Cooperative Association. Peyton?
Thank you, Ron. I work for the approximately 300 electric cooperatives that invest in research through the Rural Electric Research Program, RER for short. I should mention that most of the RER members are also members of the Electric Power Research Institute. I think that co-ops should recognize that they can take great pride in the fact that they pioneered the closed-loop heat pump technology, and that they are still pioneering the installation, the marketing, and also the research in this technology. They're trying to move it into the marketplace as our #1 utilization and marketing goal. In the research program since 1983, we have invested over $2.5 million in research in the ground source heat pump technology. That's a lot in a decade. We're focusing the bulk of our ground source heat pump research investments on reducing the cost of the in-ground loop system. We want to install the loop faster. A day is our goal. Install the loop with less impact on the landscape, and we've heard a question that points out that that is a concern. Improve the heat transfer between the earth and the pipe so that less loop would be required on each installation. A one-day installation that would leave virtually no trace of an underground loop in a retrofit is our long-term goal. We have pursued this goal by funding Jim Bowes and his staff here at OSU to produce a loop installation manual, and the purpose of the manual, of course, is to get everyone singing from the same hymn book, as Jim likes to say. so that they use good installation methods. We've also developed drilling methods, such as the angle drilling machine that Paul Steffes developed for the RER program. This machine was demonstrated around the United States and is currently down in Georgia for further evaluation and testing. The machine would have good application in a commercial application where you would want to install the loop from a single central pit, like through a existing parking lot. The drilling method is just one of the many that we've looked at. We've also looked at Charles Machine Works directional drilling machine to use in installing in residential homes without affecting the landscape. Grouting research is another area that we have pursued. We funded South Dakota State University and the University of Idaho. Of course, the goal of this research is to improve the heat transfer between the earth and the loop, which would permit a shorter loop length per ton of capacity. And we're also involved in the commercial development of the Slinky in partnership with the Electric Power Research Institute, and we're doing that work here at Oklahoma State University. In May, our Rural Electric Research members will meet to review and redefine our goals and objectives, and I fully expect that they will continue to rate ground source heat pump research and development as one of our most important goals. And finally, I'd like to encourage any individual or organization that has suggestions for ground source heat pump research to contact me directly at the National Rural Electric Cooperative Association or to talk to any of their local Rural Electric Research Task Force members.
All right, thanks, Peyton. Now, for those of you who would like additional information, you should contact Mr. Colley directly at the phone number now on your screen. Next up, we have Jim Bowes of Oklahoma State University and the International Ground Source Heat Pump Association, who will review some of the work being done on Slinky ground heat exchangers. Jim?
Thanks, Ron. The Slinky ground heat exchanger that a number of the panel members here, Bill Van Alstyne and others and Lynn Vick have talked about a new method that cuts installation costs. The Slinky was developed from a grant from 4 Oklahoma companies and the Oklahoma Council for the Advancement of Science and Technology, Climate Master, Ditch Witch, Electric Power Research Institute, and the Phyllis Driscoll pipe. And the idea here is that we were looking for an ice storage system, and the outgrowth of that came a roll of coil pipe, which has been called the Slinky, which has the promise of reducing the first cost by having a piping system that stands and is self-supported in the trench by itself. After initial evaluations in a test that was funded by the National Rural Electric Cooperative Association and Peyton Colley here, we decided that looking at it that we knew a lot about the technology, but that we didn't know how to transition from one type of coil to the other, what problems we would have with backfilling, what it would take to make this a successful project. We knew in a lot of applications things were going very well, and we wanted to continue that research and make sure that those benefits would then be transferred to other locations throughout the country. So the tasking was to go ahead and do the research on one contract. Another contract was to write those development or design guidelines for installing these systems, and so that's what we've done. I think we can look at cutting trench lengths by at least half and maybe labor costs by half. You saw Lynn Vick, or you heard Lynn Vick say that one person out there with a trencher is able to do the trenching and install the Slinky by itself, so we're looking at increasing our productivity. Research that's funded by both EPRI and NRECA is not only here at Oklahoma State University, where we're doing certain studies. Dr. Marvin Smith is responsible for that, and if you have questions about that, you can't get a hold of him, well, you might try me. At the University of Kentucky, we have Dr. Bill Murphy, who's doing the work there. And just as important work is the grouting and the backfilling that's done by Charles Raymond at South Dakota State University. To show you the range of applications that are operating today in the climate that we have is that we have a number of these in Minnesota where they have 10,000 degree days. Pete Everhart up there decided to put these things in and probably got us started a year or two before we had planned. In Pennsylvania Power and Light folks, Mike Messer and Bartosik are looking at laying these Slinky type coils horizontal in trenches, in wider trenches where the soil is not self-supporting and wider trenches have to be dug with backhoes. All in all, I think the research is progressing as we would hope. We are looking at those concerns that you heard Lynn talk about earlier, backfilling, type of soil, moisture content. The work really looks good, and the last time I talked with some of the people up north, they were having loop temperatures in the mid-30 degrees. So that's a pretty good summary, I think, of what the state of the art is right now.
All right, thank you, Jim. Dr. Carl Hiller of the Electric Power Research Institute manages projects that include the development of a non-toxic antifreeze solution, as well as using geothermal heat pumps for water heating and building capacity modulation in geothermal heat pumps. Products that result from these studies should further reduce overall operating expenses and improve comfort and load shape characteristics at the same time. Dr. Hiller's here in our studio to tell us about these developments. Dr. Hiller?
Thank you. In this age of growing awareness of environmental impacts, EPRI and others recognize that it would be beneficial to have an antifreeze available that would have minimal effects on the environment if the ground loop were to be damaged in some way. As a result, we have worked with Cryotech Corp to develop a new antifreeze called GS4, which is a mixture of potassium acetate and proprietary corrosion inhibitors. This material was originally developed for airplane de-icing and had already passed stringent tests of its effects on the environment. GS4 also provides reduced pumping power requirements and improved heat transfer characteristics compared to currently available alternatives. In the area of water heating, it is important to recognize that domestic water heating can be provided much more efficiently by using vapor compression technology than by conventional methods such as electric resistance or fossil-fired water heaters. Vapor compression technologies, and by that I mean heat pumps, air conditioners, or refrigeration equipment, provide water heating at efficiencies greater than 100%, typically on the order of 200 to 300%. This is because they use the heat pump principle. In some situations, by using waste heat, for example from an air conditioner or refrigeration equipment, vapor compression systems can provide totally free water heating. Vapor compression water heating can be done basically three ways: de-superheater water heating, the use of dedicated heat pump water heaters, or what we call multifunction full condensing water heating systems. De-superheaters, as shown in this diagram, are refrigerant to water heat exchangers installed on the outlet of the compressor and are designed to use about 10 to 15% of the available heat in the refrigerant gas for water heating. De-superheaters have the advantage that they can be added to any vapor compression system, either by the manufacturer or in the field, and can provide much useful water heating. A drawback is that they only provide water heating when the system on which they are installed is operating for its originally intended function. A backup water heating means is needed at other times. For example, a de-superheater on a space heating and cooling heat pump cannot provide water heating in the spring and fall when neither space heating or cooling are required. De-superheater water heaters are readily available today from manufacturers as factory-installed options from many ground source heat pump equipment manufacturers. Dedicated heat pump water heaters, as shown in the next diagram, are heat pumps specifically designed to heat water. They can be used anywhere, regardless of the type of building space heating and cooling system, and they provide high-efficiency water heating year-round as compared to de-superheaters, which only provide it when their equipment to which they are installed is operating. They provide free cooling and dehumidification in the summer, and even if they use conditioned indoor air as a heat source in the winter, they provide water heating at a high overall efficiency as long as the space heat is also provided at high efficiency, such as it is, for example, by a heat pump. One drawback to dedicated heat pump water heaters for residential applications has been their higher cost compared to conventional alternatives. EPRI has been working with manufacturers to develop lower cost products. One such new low-cost heat pump water heater should be on the market in late 1993. Multifunction full condensing water heating systems, as shown in the next schematic, incorporate an additional condenser, allowing them to provide standalone water heating ability in addition to their other functions, such as space heating and cooling. As a result, they also provide high-efficiency water heating year-round. Multifunction full condensing systems must be factory designed with the necessary features, and care must be taken in the design to maximize their efficiency and reliability. Several versions of air source heat pumps are now on the market with full condensing water heating ability. EPRI is currently working with suppliers of ground source heat pump equipment to develop the multifunction full condensing features in ground source heat pump equipment. These new products should be on the market in 1994. Another area of rapid development in heat pumps is capacity modulation. Capacity-controlled heat pumps through the use of multi-speed or variable speed compressors or multiple compressors are very advantageous for both efficiency and comfort reasons. For example, as shown in this figure, a system having a 2-speed or variable speed compressor can be sized to reduce or eliminate the need for auxiliary heating and can run in low-speed mode during air conditioning to provide good comfort and humidity control without excessive on-off cycling. Operation in low-speed mode improves seasonal efficiency, reduces cycling losses, reduces noise and temperature swings, and improves overall comfort. Advancements in capacity-controlled heat pumps are proceeding rapidly. EPRI worked with Water Furnace International to develop the Premier AT Series 2-speed heat pump with optional desuperheater water heater, which was introduced to the marketplace in 1992. Numerous other 2-speed, variable speed, and dual compressor systems are expected on the market in the next few years.
Thank you, Dr. Hillier. For those of you who would like to know more about these developments, you should contact Dr. Hillier directly at the address on your screen. Because geothermal heat pump technology is relatively new in some regions of the country, training for the design and installation of ground source heat pumps is a high priority of the industry. The International Ground Source Heat Pump Association, headquartered at Oklahoma State University, has developed a series of design manuals and training programs. The details of these programs will be addressed by Dr. Jim Bowes. Jim?
The International Ground Source Heat Pump Association has developed a series of training manuals and workshop curricula and accredited training programs. The training and design manuals include the Closed-Loop Ground Source Heat Pump Installation Guide, Thermal Properties of Rocks and Soils. It's a field manual supported by the Electric Power Research Institute, and also a grouting manual for the vertical boreholes. And a train the trainer curriculum so that we can train trainers that can go out and train accredited installers throughout the country. For residential design computer software is available from the various heat pump manufacturers and also from the International Ground Source Heat Pump Association. For commercial buildings, software recognized by the International Energy Agency is also available from the association.
All right, thanks, Jim. Well, most of the materials that Jim told you about are listed in the catalog of IGS HPA materials included with the packet at your downsite today. Understand this has been a great deal of new information for you, and in order to answer your questions, we're now going to open the program back up to a question and answer session with our studio guests. We have some questions that have come in while we've been hearing other presentations and viewing tapes. This one is open to anyone. It comes from New Jersey. Actually, two questions. First, have you found greater, equal, or less profit margins with ground source systems compared to fossil fuel, such as gas? And can you share those percentages? And which GSHP system has the greatest acceptability and profitability? Who would like to tackle that one? Bill, looks like you're ready.
Okay. Well, actually, it'd be hard for me to answer the first part of the question because my firm deals just directly, solely on earth-coupled heat pumps and has from the beginning. As far as profit margins, I would say the horizontal system, our horizontal installations are a little bit less expensive to do than the vertically bored systems. Basically, we have about the same markup or profitability in the horizontal versus the vertical. We do about 50% of our business is in the horizontal, 50% in the vertical business right now. And we try to maintain about the same profitability both ways. If the units are installed correctly, then we very seldom have problems with earth loops in either situation. Maybe Lynn could give you further information, the difference between gas and electric.
As far as the profitability goes between gas and electric, we make the same markup on ground sources that we do gas equipment or air source equipment, whatever we were putting in before. A lot of it, you can make more the longer you're in the business because you can do them faster. Another aspect is in my area, I don't have a whole lot of competition to deal with. I can determine the price of what I'm going to put the systems in for.
Ralph, you want to add to that?
Well, of course, I'm just a loop contractor, and what we've specialized, or the arrangement we have, is with HVAC contractors. It's my understanding, especially one of my better contractors in Houston, Texas, that the profit margin is better in the water source than it is in the air source. Of course, we focus to a different clientele, and you have to know how to sell the systems. And he's able to successfully sell the system, and as a result, get what he asked for. And we're doing some real large homes there in the Houston area, one being 75 tons. And I think one of the things that the people that can afford this type of thing do is they brag on the fact that they have something that someone else doesn't have. I mean, obviously they can afford the utilities, but you know, the aesthetics and the fact that it's a very simple system with very little maintenance is very attractive.
All right. We have another question called in, referring to one of the videotape segments we saw. It says the picture on the Baton Rouge site in the machine room doesn't have a return hooked up to the units. Is this a usual practice on a large job over a residential? And if so, where do they get their return?
Was that on the ducting system? The return is bound to have been on the air side.
Right.
Well, sometimes in larger commercial buildings, they use the ceiling area as their return air, and that is considered a plenum. And it's what's commonly used in some of these larger applications because of the return air. They just have return air grills in the ceiling and then have diffusers in the ceiling to distribute the conditioned air.
All right, thank you. We have a load of questions that have been called in. Dr. Hiller, I have one for you. Is GS4 accepted by EPA and local code authorities for use in heat exchangers that come in contact with groundwater?
It's my understanding that it's been accepted by a number of states. It takes a little longer to work through the acceptance process in the federal system, and things look very promising, but they are not yet totally approved in the federal approval procedure.
All right. Call from North Carolina, or a question from North Carolina. Jim, you may want to tackle this. Is it harder to purge air out of slinky as opposed to vertical loop?
The question was, is it harder to purge the air out of a slinky versus a vertical loop? And if you don't know what you're doing with removing air out of a header system or a slinky, it's going to be harder, but you can overcome that with a larger purge pump. But if you design the header for air removal and you get a large enough purge pump, the air will come out of there. Naturally, I would say that you could design a header system for a vertical system that would be just as difficult and maybe even more difficult than a slinky. The important thing is that you go through something like the design installation guide manual that we have, or talk to some people that know how to design headers so that the air will go out, and you can save yourself a lot of trouble. They're about the same if you know what you're doing. If you don't, you can have some grief.
Okay. We're going to keep you on the hot seat. We have a call from Burlington, Vermont. Is there an association that will certify contractors to do this work?
There is the association, the International Ground Source Heat Pump Association, certifies installation contractors either through workshops at several universities like the University of Kentucky, Oklahoma State University, but you can also get that same certification training from the heat pump manufacturers. And that their trainers go through the program that was developed by the association and is managed here at Oklahoma State University, called Train the Trainer. And these trainers come in for 5 days. They go through heat fusion, they go through purging, they go through design, they go through duct design, which is very, very critical in any system that you install. So they go through the whole range: grouting, backfilling, slinkies, boreholes. We give them, so the mechanism is there. If you want to become a qualified trainer as part of the Train the Trainer, you'll need to come to Stillwater. If you want to become a trainer or an accredited installer, then you can do that through the heat pump manufacturers.
All right. Peyton, we have a call for you, or a question for you from Pennsylvania. What about using a pneumatic gopher or weasel when installing underground lines with minimal lawn restoration?
Well, we've looked at a similar technology. I think that the pneumatic weasel they're talking about may be something like the mold technology, that they use water jets to clear a path and then pull cable behind the mold device. We've looked at the Charles Machine Works angle drilling rig that you can actually pull up in front of a urban home with a very small lot and drill at an angle underneath the home, come up in the backyard, and then pull the loops into the hole that you made in the backyard. This makes a very small mess as far as, since everything's up at the curb and they can take care of the mess cleanup where the equipment is. It has a great deal of potential. The biggest problem we have is that contractors think in terms of we've got to make $15 per linear foot in order to be profitable, but they're thinking where they normally go in and they spend a day putting in a single service drop for a gas or an electric hookup. The biggest goal is to get contractors to think in terms of doing systems where we're talking about several hundred feet of borehole to be very productive, to put the system in quickly, and to do it at a competitive price. These contractors we have sitting here, you've heard the stories they're telling about their attitude towards installation, and it's not on a per foot basis, it's on a per job basis, and the installing contractors have to learn to think in the term of moving towards a total installation cost and away from a per foot drilling cost. And you know, drilled systems are one thing that we're spending a lot of development work on because, as Lynn pointed out, sometimes yard restoration is a problem, and so there'll always be a place for drilled systems and the fact that they can be made not to impact the yard very much.
Thank you. Lynn Vick, we have a question for you from Pennsylvania. Wanted to know about cold weather, freezing and thawing and all of that. In the northeast winters, would that cause a problem with underground piping?
When you're designing one of these systems, you need to, when you're designing the ground loop part of it, you need to use the best pipe available on the market to put in the ground. If you use the good high density polyethylene pipe and put it in the ground, you should never have any problems with any kind of weather or any kind of ground conditions. I've never experienced any pipe problem whatsoever. In the last 8 years that I've been installing these, I've never had one pipe failure or one problem with the pipe.
Bill, a question for you also from Pennsylvania. What about clay soil and rocky conditions? Do they add to the final cost?
If you're doing a horizontal system, if you have clay soil or rocky conditions, clay soil is not so bad. If that may slow your trenching process down. The contractor should take that in consideration when you're doing your trenching. If it's rocky, that could adversely impact, of course, your ability to trench. In this case, you may want to drill or to maybe take samples of the ground as you're going to make sure that you can trench in that area. If it's the type of rock that you can trench through or backhoe through, whichever, you'd want to be very careful about your backfill, possibly backfill with sand around the pipe immediately and try to weed out as many of the rocks as you can so that you get a good backfill and you protect the pipe from any more damage than possible. What we worry about is just rolling a boulder on it and pinching it off or cutting it in that manner, not so much its movement in the ground.
Thank you. Dr. Hiller, question from New Jersey. Under the new EPA ruling on CFCs and HCFCs, how will this affect the efficiencies of units, and have they been tried with alternative refrigerants?
Of course, that's a very important issue that's on the forefront of the HVAC industry. Most of the current ground loop heat pumps use HCFC 22 as a working fluid, and that is going to be phased out probably in an accelerated manner in the early 2000s. There are a number of viable alternatives being studied around the country right now. Replacements for R12, I think they're zeroing in on R134A as a working fluid. I think overall from an efficiency standpoint, by the time you re-optimize the compressors and the heat exchangers to work with the new working fluids, I don't think we're going to see a major efficiency impact. There might be a little bit of a cost impact.
Second follow-up question from that same questioner. If glycol leaks or spills into the ground, will this cause EPA cleanup problems?
I'm not sure I know the entire answer to that. Some of it has to do with the historic uses of glycol, more so for automobile antifreezes and truck antifreezes. There they tend to pick up heavy metals while in use, And due to great measure from the heavy metals present in those applications, they are sometimes classified as a toxic waste. I don't think they're going to pick up the heavy metals to anywhere near the extent in a ground loop installation, but the regulations may inhibit those standard glycols in the future because of their other applications.
Good. Jim Bowes, a question for you from Missouri. Wants to know about installing a horizontal sling under a septic lateral system.
Well, the natural reaction is to save some money by going underneath the septic system laterals. The one benefit going underneath there is that you can be guaranteed that the soil is going to be wet, which will have a higher thermal performance. The other thing is that you brought two different regulators into the picture with you. You now have the heat pump installer, and now you've got the people that are responsible for the waste systems. Our experience has been the requirements by the waste people that you backfill with sand and you have certain other grade requirements. It makes it a little bit more trouble than is really profitable. It is better, but there's all those qualifiers that go with it.
Thank you. Peyton, question for you from New Jersey. They want to know if GSHP is just another name for a geothermal heat pump, and if yes, was it changed for marketing reasons?
Well, there's been a lot of debate about what we should call ourselves. The ground source is kind of a compromise so that we don't exclude the water source people or any other technology aberrants that we have. The correct name, I think, for what we're talking about today is really closed loop. You know, it's closed loop that's getting energy from the earth, but ground source kind of keeps everybody else in the ball game.
Jim, back to you. Same caller from New Jersey wants to know what the typical efficiency is of a system, and are there ARI ratings, and if not, why?
Typical efficiency for these systems, and then you mentioned ARI. When you say ARI, you're talking about the heat pump efficiencies, and yes, they are available for all the manufacturers of the heat pump equipment. Now you're going to hook a source to that, and so the efficiency of that is controlled by the design of the ground heat exchanger. And so you can, depending upon what your design objectives are, that Dr. Hiller is pressing this gas industry for, depends on what the design objectives are of the project, what you want that ground heat exchanger to be. If you want to cut demand, you want to cut lower utility costs, well then you will make different decisions in the design. All of those things would then impact in the system efficiency. So, you put more pipe in the ground, it's better, it costs more money. So you have all of those things to contend with. But the opportunity is there to kind of control that efficiency as to where you want it to go. But the heat pumps are rated by ARI.
Final question from this caller wants to know how many different manufacturers there are.
How many different manufacturers of water source heat pumps? Mm-hmm. Oh, I'm aware of 8, 9, 10. Some of them are not rated by ARI yet that are very good, but as an industry, I think we've kind of held the line that says, we'd like to see you send your equipment up there and have it tested, in a no holds barred situation. So there are those, but there's some good equipment out there that isn't rated, but it's difficult, to pass that on to electric utility that has to have some sort of standard. And to a homeowner, they want to know who's watching over it for us.
All right, thank you. This is directed to our contractors. It comes from Elizabethtown, Kentucky, and they must be worried about the New Madrid fault. Wants to know how earth tremors and earthquakes would affect ground loops.
Well, I think that's a good question, a valid question. I think one of the reasons we're using polyethylene pipe is because the gas industry sees fit to use it in California. And we all know that California is fixing to fall off. But it's a good application for this pipe because it has good stretch applications to where it won't. It's very overrated for what we're using anyway. We're using 160 psi rated pipe and we're only putting 60 psi. And you can stretch the pipe and still not affect the integrity of the pipe to any great extent.
Bill or Lynn, do you want to add anything to that? Or?
As as Ralph mentioned, the pipe can stretch, I believe it's like 8 times its length before it finally would fail or break. Of course, now if it stretches that much, you're going to have some slight restriction in it, maybe a great restriction, but it would take quite a fault or really a massive disaster to really affect the pipe. And again, consider that you're usually in the confined area. You're not stretched out over you're not stretched out over a football field or something like this, where unless it's a large commercial installation. On a residential installation, it's usually a very small block of land that you're talking about, and so the pipe is well suited for the purpose it's being used as.
Thank you. Dr. Hiller, another question. If the loop lasts 75 to 100 years, does the antifreeze last as long?
As long as it's not exposed to air, it should last quite a long time. It's when you start getting air back into the system for some reason. The antifreezes are equipped with inhibitors to take some of the oxygen out of the air so it won't corrode the pumps, etc. But it shouldn't degrade unless there is oxygen present, and in a totally sealed system without makeup, it should last a long time.
Jim Bowes, can you use an existing well for household water supply? Questioner from Pennsylvania.
If you have a water well, I'm assuming that you have sufficient water to run a heat pump, and you can figure somewhere around 2.5 to 3 gallons a minute per ton. And when you're talking about a typical residence in our part of the country, you're talking about 1 or 2 million gallons of water a year. Now, if you've got an aquifer that will support that and it's non-corrosive and it can be discharged, you should go for it. There's a lot of areas in this country where they have tremendous amounts of water. Oklahoma's one of them today, believe me. We have more water than what we need. But yes, you can use an existing water well. Now, people will attempt sometime to put a closed loop in that water well, and that has worked in some areas. Carl Oreo in the Northeast has what he calls a hybrid system or a bleed system, where he uses the advantage that you're bringing in warmer or water into a borehole, and you're discharging that out. So that means you've transported the heat into the well bore field, and he's had some very good success with that. So there's a lot of different designs out there that are working very well, and I think the most important thing is to talk to somebody that's had that experience before you launch off on your own. Don't put in 100 systems before you know what the first one's going to do.
All right. Peyton, we have an unidentified caller here who asks a couple of questions. First, why is so much of your research focused on drilled systems instead of on horizontal systems?
I guess we're looking for the equivalent of a drilled slinky. You know, I think the slinky is going to solve a whole lot of our competitive problems in terms of horizontal systems, but horizontal systems can't go everywhere. They can't really address the needs of a commercial building where you have a large cooling load and the building is sitting on a small lot. A lot of urban homes have very small lots and they're well landscaped, and people are just not going to tolerate someone coming in and trenching up their well landscaped yard, no matter how good the restoration is. So we're looking at drilled systems to fill the need in the market for something other than the surface installed loop system. Another reason is that as you go in commercial installations, and I'm sure Ralph would agree with this, that you just can't get the capacity without going in a drilled system. Probably drill systems will go a lot further once we find thermally enhanced grouts to enhance the heat transfer between the pipe and the soil. And once we convince, I think more than anything, once we convince the installing contractors that they can make money installing these systems without thinking in terms of $6 or $7 a linear foot, that drilled systems will get a larger share of the market. But another reason really is that solving the problems in the drilled system industry are very difficult. And that's really the role of research, as we try to tackle the difficult problems and spend our research dollars where no one else will. And so I think that's part of it, is that we're trying to work with a very difficult issue and try to find solutions where none may exist, but we're going to certainly take a look.
Great. Dr. Hiller, does the installer need to change any installation practices to use GS4, Teflon tape threaded compounds?
The Potential for leaks, especially in threaded fittings, is something that you have to pay attention to. Conventional Teflon tape probably won't be good enough. There are a number of other paste-type materials that can be used. We have currently ongoing tests in that regard to see what thread sealant materials are better than others. And you have to pay attention to details to how well you torque up your threaded fittings. The threaded fittings and the flange fittings are the most important ones. It does leak a little easier, which is part of why it has lower pumping power requirements, etc. It's a little thinner. But I think those are all solvable problems, and in short order we'll have recommendations on what sealants to use.
I have a call from Iowa, and this is addressed to Lynn and to Bill both. Do HVAC dealers recommend annual maintenance contracts for GSHPs? Service contracts, in other words?
My firm does not. We don't recommend it on the ground source heat pumps because we just have very little maintenance to do with on those units. So generally speaking, we do not do that. Even on our commercial installations, the light commercial installations, because they are individual units, we haven't found that necessary.
We don't require any service contracts. There's virtually no problems with the ground source. Only maintenance is change the filters regularly. Other than that, that's about the only maintenance required on one.
Very good. Jim Bowes, we have a call from Binghamton, New York. They want to know who absorbs the cost of sizing the job, the time involved, for instance, and what are the costs of the training materials? Two questions there.
Who absorbs the cost of the design? If it's a residential design, generally the installing contractor will have a knowledge of that, and he's been trained to do that. I know Bill has that knowledge to design. Lynn, Vic also has that knowledge. The cost of training can be very, very high if you do one incorrectly. That's the cost of training. Now, you know, a week in Oklahoma, the airline ticket and train the trainer, you're going to drop a couple of $1,000, but you may save that on the first job. I'm not necessarily I'm promoting our program here, which is exactly what I'm doing, but what you get when you come to some of this training is the experience of the whole class. The people that come to these now have changed dramatically from what they were 5 years ago. 5 years ago, had a lot of do-it-yourselfers. Now we have contractors that come in and that know the business, are looking to see if there's anything left on the table for them to pick up. I was at a contractors meeting in Pennsylvania offered by Penelec, and they had people in there that had installed hundreds or maybe thousands of boreholes, drillers, wanting to find out, is there something here that we don't know? So training doesn't cost a lot of money, it's a benefit. And I think that there's so much new technology. You know, you have the air removal, you have the grouting, you have the antifreezes, you have all of those things which impact on the design and can save you tremendous amounts of money. I don't have to talk to Bill and Lynn about this. They are part of the development. They're in there, and I go out and watch them operate so I can steal their good ideas.
We have a call from Oregon. This is directed to any of our contractors or to Jim Bowes. When installing a closed loop in an open pit, say 100 feet by 80 feet, how do you recommend fastening the pipe in the loop to keep it evenly spaced?
Well, I think some of the pit-type heat exchangers that I've seen in Minnesota and the work that they're doing in Pennsylvania and other locations is that when it's laying flat, it's fairly stable. It's in a configuration that it was shipped in. It's a pipe roll, and so the slinky is a series of rolls being laid flat. So in a pit type, you know, you could kick some sand on the top of it. You could, you know, put anything that's not sharp or abrasive around it. But generally, those go in very, very easy. A lot easier than those that go in the narrow 6-inch wide trenches, where the real challenge there is to backfill around it when you're in a moisture condition with your backfill. That's just really a challenge. That makes the old pros really groan.
Tim, want to add anything to that?
Well, I think a bent, something like in a line of a bent welding rod, to be able to just, you know, push it into the ground to hold it while you're putting backfill on, because it's going to have some movement as you put dirt on, unless you drop it directly on top. So, you know, any heavy gauge wire bent over like a horseshoe, just shoved into the ground would hold it in place.
Good. Dr. Hiller, are GSHP with water-to-water heat exchangers currently available to exploit efficiencies of in-floor hydronic systems?
Yes, there are several manufacturers that make water-to-water heat pumps, and they can be applied in geothermal installations, not only for the use of hydronic in-floor heating, but also for providing domestic hot water directly from the loop in a dedicated heat pump water heater fashion.
A question that's open to anyone comes from Ohio. This individual, in installing a loop system, hit an old mine shaft, and they want to know if the mine shaft can be used in any way for the GSHP loop system.
I would say it depends if it's full of water. If it's full of water, yes, you could, because obviously it's very difficult to transfer heat into the air, and that's one reason why we're going vertically and getting into heavy saturated soils, is to take advantage of the high density. If that mine shaft were full of water, or even if it had water in the bottom portion of it, you know, if you could get a heat exchanger down in there, it could be used. Of course, you're going to have to address a problem of potential contamination from the surface, and I think that would have to be addressed, and also potential of caving in. That'd be, I think the state authorities would probably want to know about this.
Anyone else care to add anything to that? Okay. Jim, a question from Paducah, Kentucky. What's the centering water temperature supposed to be during a normal winter and summer season?
The entering water temperature? The question was, what's the entering water temperature supposed to be in the summer and the winter? Well, you'd like to have it in the wintertime as warm as possible, in the summertime as cool as possible, but there are economic constraints. A guideline that we try to use for the minimum in the wintertime at any location would be 40 degrees warmer than the coldest outdoor air temperature. So in Oklahoma that might be 37 degrees, in Minnesota that might be 25 degrees, but now we're seeing slinkies that are running 31. In the summertime we'd like to hold those maximums down because we think demand reduction and efficiency are important. We'd like to, in our area where it gets up to 105, 110, we'd like to hold it at 95, and we'd like to encourage Lynn and these other people to try to sell even more pipe and get that down into the 85s. There's a lot of things, but I would say offhand that you're 10 to 15 degrees cooler than the hottest outdoor air temperature is typically where the design started. And then the negotiations begin after that about efficiency, demand reduction, and that whole caveat of opportunities.
All right. Another question for you, Jim, from Indiana. Maintaining pressure in the loop system, they've had several problems with pressure, and they would like you to discuss extensively about this.
Well, they want an extensive answer. I don't think these other guys will put up with that. If you're losing pressure in a loop, you most likely have a leak, or you've got a lot of air in there. But if you have a leak, you know, the most difficult leak to find is one that does not appear at the surface of the ground heat exchanger or in the equipment room, and is so slow and so small that it evaporates. I cannot imagine if you pressurize one of these things up to 60 pounds pressure in the wintertime that you should have any problem after you've done that either once or twice, other than being a leak. Bill, can you imagine what could cause the pressure to fall?
No, that would be, you'd have to have a leak either under the ground or above the ground, one or the other. If it continues to leak, if you've done this several times, your only alternative is to go back and to put what we have talked about before, is put a makeup water device on it, maybe a pressure regulator, something off of a potable water line. You want to make sure that you inject as little of this as possible, but it may not be a real big concern. If you understand that, for instance, a 5-ton slinky, or let's take a 5-ton vertically bored system, it may not hold but 100 gallons of water when it's completely full. And the difference between 60 pounds of positive pressure on that system and no pressure, 0 pounds, is as little as a quart of water. So we're usually, in this case, you'll be talking about a very minor leak, something that you might not ever be able to find. In that case, you would probably have to live with a water makeup device attached to the system. That will do two things. It'll maintain pressure on it, and if the leak is such that it gradually could get worse, it's going to show above ground where it's at, then you can attack that problem. If not, you may not ever have another problem with it. It's not something that under normal circumstances that you'd have to worry about, you know, what is 2 or 3 gallons of water in a year by trying to re-landscape the lawn if you have a very minor leak like that. But basically, if it's going down after you've pressured it once or twice over a year period, then you've got a leak.
Peyton, Carl, question from Cleveland, Ohio, aimed at or directed to both of you. Is there research planned into advantages and disadvantages of direct expansion technology? Carl, you want to start off, and Peyton and follow up?
We have looked at direct expansion. I believe in '86 was the first time we looked at direct expansion in Ohio. We looked at direct expansion in Indiana. We had load research on the Indiana project, and we were expecting to find significant energy efficiency increases, you know, lower kilowatt hour usage in the use of direct expansion because you do away with one intermediate heat exchanger. We didn't find any real large energy savings. Really, we couldn't determine there was any energy savings over a regular plastic system. But what really came along and kind of put a fly in the pie was that the government decided to regulate the refrigerants, and of course the refrigerants in a direct expansion are put directly into the in-ground loop. And so we had to kind of take a political stance that the larger refrigerant requirements that direct expansion needs in order to operate was going to be a problem as the price of refrigerants increased, and the ability to get the refrigerants in the future became a problem. So we decided that we would back away from the direct expansion until a couple of things happen. Really, one is until they come up with satisfactory replacement refrigerants, and then we may go back and revisit the installations we have. And also until we've had a chance to see what happens to the copper in the ground. The utility industry has been putting wire in the ground for a long time, and when you put wire in the ground or copper in the ground, you have problems. And we want to see what sort of problems we have over a long term, maybe 10 years, maybe 20 years, with direct expansion systems where you use metallic heat exchangers. And once we've had a good long period to review the effects of using a copper in the ground heat exchanger, then it may be we'll come back and revisit this technology.
Carl, anything to add?
Well, let me just review briefly the advantages and the disadvantages of direct expansion ground coil technology. Direct expansion ground source heat pumps do offer the promise of higher efficiency because they eliminate one stage of heat transfer. What we see in the field in most applications, however, is instead of actually achieving that higher efficiency, the higher cost of the ground coil, because it's made out of copper instead of plastic, causes them to not put in as much ground coil, and therefore you don't see the efficiency benefit that you would expect to see. Also, there are certain soil types where you can't put copper in the ground. It will definitely dissolve. Other soil types will hold up just fine. The CFC issue was an important consideration. I think the CFC issue, the refrigerant issue, will be mitigated in the future, and there will be acceptable refrigerants for use in ground source heat pump installations again. We're keeping an eye on that technology. Right now we have no ongoing efforts. We have been involved in field tests in the past, and if things change around, we may do more on it. Right now it takes a more experienced installer to install them. There's a lot more refrigerant to deal with, a lot more in-field refrigerant piping connections to be made, and you got to pay more attention to detail to get a good installation, and that may mean overall higher costs, but we'll keep an eye on it.
Peyton, you want to add to that?
Yeah, I think that one of the big advantages in the political and regulatory climate we have now is that the fact that a regular water-based ground source heat pump has a very small refrigerant charge. It has a much smaller refrigerant charge of like 1/4 that of an air source and less than a direct expansion. It gives us a great advantage in the eyes of the regulatory agencies. And also, if alternative refrigerants are developed, you can expect them to be more expensive. And so that lower charge of refrigerant in each individual unit is going to be a factor for a long time to come. And that really is a lot of our basis. The other thing that Carl pointed out was that it requires silver sorter connections basically with the refrigerant lines, And I spent 10 years as a contractor, and I can tell you that getting the field connections done in a proper manner is a very difficult thing. Very few contractors use nitrogen when they open the copper system, and it's just a much more difficult area to deal with. And so our industry represents, I think, the closed-loop packaged units that use plastic heat exchangers, and that's kind of the direction we've elected to pursue for a few years, and I think we'll continue on that path.
Good. Jim Bowes, some question from Pennsylvania. Could all types of sand be used for backfilling of a slinky loop? Would silica sand cause heat transfer problems?
Well, silica sand would be the best. It has a higher density and it has the higher heat transfer rate, so that would be better. What we would like to see in the sand like that is to have a large number of grain sizes so that all the air voids are filled with soil particles or sand particles. So anything that packs well around the pipe, has a large grain size distribution would be acceptable.
A couple of other material questions, these from Kentucky. What's the very best material to grout the vertical bore back in, and which material is best to fill the vertical bore from the bottom up, and how well does it work?
Well, you're asking the professor about what a driller knows a lot about, and you have two guys that are licensed water well drillers here. What is best? I think I'd ask Ralph Cadwallader over there, because he's probably pumped more grout than I'll ever see.
Ralph, he's passed the ball into your court.
Well, that was a tough one. I was hoping we could avoid that all day today, but it's inevitable. I think that it's a critical issue because we have, as a water well driller, I'm concerned, as I started as a water well contractor, I'm concerned about protection of the aquifer because that is one of our natural resources. It's very precious to us as a nation. We need to protect it, and I think we're committed to that. And as a contractor, I've got to be committed to that, not only to stay in line with state regulations, but also because of the fact that it is and can be a very big problem. I feel like, and it's a personal issue with me, that each individual job is different. The geology that we drill through is very different. It's obvious, as you saw in some of the film, that we have some very difficult situations. And it really, I don't have enough time to get into the grouting right now, but I think it's very critical. I think what we need to do is either meet or preferably exceed state standards. And if you can do that and still get your heat transfer, I think you'll accomplish what we're trying to do. And let me stress, exceed. I think some of our states are lacking behind. Some don't even have regulations, but I think it's soon to come.
You bring up water quality concerns, probably our last question. We're running quickly out of time. This comes from Albany, New York. Jim Bowes, this is directed to you. Want to know about government position on the use of open loop systems having emphasis on pollution of aquifers, and will the open loop be banned as a result?
Oh, I think in some areas where water shortages may occur, you could see that, but right now we have a lot of areas where that does not exist. Open systems, what we call pump and dump, are very viable, non-corrosive, place to discharge it, and the local authorities are in tune with that. They're very viable, and there's a large number of those out there in the country right now. It's a ground source type along with direct expansion and closed loop.
Jim, thank you, and gentlemen, thank you for all of your participation, and thank you also to our viewers and your many questions. As you can see, I still have a stack we didn't get to. If you have additional questions about this program, please contact the sponsors directly through the PRA at area code 703-742-8402. Your comments and to the sponsors and organizers of these conferences. We'd ask you to please fill out the conference evaluation form and questionnaire in your packet and return it to your downsite coordinator. Downsite coordinators, we'd like to remind you to please mail your registration lists and evaluations back to PRA. Remember, the next scheduled teleconference is for architects and engineers. It will be on April 28th. We hope to see you at that time.